Welcome to this scientific lecture on croissants, where we explore lamination, plasticity, and gas-driven puffing in layered composites. Here we see the characteristic layered structure of a croissant, with alternating layers of dough and butter creating a complex composite material. Let's begin by understanding the fundamental concept of lamination in croissant production. Lamination is the process of repeatedly folding and rolling dough with butter to create multiple distinct layers, similar to engineered composite materials. The number of layers n equals 3 to the power of n, where n is the number of folds, using a traditional three-fold technique. With each fold, the number of layers multiplies. One fold gives 3 layers, 2 folds give 9 layers, and this progression continues exponentially. A traditional croissant uses 6 folds, which creates 729 distinct layers of alternating dough and butter. Mathematically, 3 to the 6th power equals 729 layers. You might ask, why not do more folds to get even more layers? There are physical limits to this process. With too few folds, layers are too thick and don't create the characteristic flaky texture. With too many folds, layers become so thin they merge together. The success of lamination depends critically on butter plasticity, which is temperature dependent. The optimal temperature for butter during lamination is 15 to 18 degrees Celsius. Butter plasticity follows a curve with temperature. At the optimal range, butter is pliable but not melted, allowing it to spread evenly without breaking or liquefying. Below 10 degrees Celsius, butter becomes too hard and brittle, causing it to fracture and break through the dough layers. Above 20 degrees Celsius, butter softens too much and begins to melt, causing it to be absorbed into the dough and destroying the distinct layers. The viscosity eta as a function of temperature follows an Arrhenius relationship, with eta as 0 times E to the activation energy over RT. Butter consists of approximately 80% fat, 16% water, and 4% milk solids, each contributing to its unique properties. The dough layers contain gluten, a protein network that provides structure and elasticity. Gluten forms from 2 proteins, gliadin, which provides extensibility, and glutenin, which provides strength. The gluten network forms a 3-dimensional mesh of interconnected protein strands that trap gas bubbles and provide structural integrity. Kneading for 5 to 8 minutes develops optimal gluten structure. Too little kneading results in weak dough, while excessive kneading makes it tough. In rheological terms, the storage modulus G' must exceed the loss modulus G" for proper elastic behavior. Cold fermentation for 12 to 24 hours allows enzymes to break down proteins gradually, enhancing both flavor development and dough extensibility. During baking, complex heat transfer drives the transformation from raw dough to flaky pastry. Heat diffusion follows the heat equation, where temperature change over time equals thermal diffusivity alpha times the Laplacian of temperature. Heat flows from the oven into the croissant from all sides, creating temperature gradients that drive water vaporization and layer separation. Croissants are typically baked at 190 to 200 degrees Celsius. Standard baking time is 15 to 20 minutes, during which multiple physical and chemical transformations occur simultaneously. The key mechanism for layer separation is water vaporization, which creates steam pressure between layers. Liquid water transitions to water vapor at 100 degrees Celsius, undergoing a phase change. Steam volume is approximately 1,600 times the volume of liquid water, creating enormous expansion pressure. Before baking, layers are thin and compressed. After baking, steam expansion separates the layers, creating the characteristic flaky structure with gas pockets. The ideal gas law relates pressure to temperature. As temperature increases, pressure increases, forcing layers apart. Croissant dough contains 35 to 40% water by weight, all of which contributes to steam generation during baking. Different temperatures trigger different transformations in the croissant during baking. At 60 degrees Celsius, yeast cells die, ending fermentation and CO2 production. At 70 degrees Celsius, starch granules absorb water and swell, beginning the gelatinization process that sets the structure. At 100 degrees Celsius, water boils and vaporizes, creating the steam that separates layers. At 140 to 160 degrees Celsius, Maillard reactions occur on the surface, creating the golden brown color and complex flavors. This graph shows how different transformations occur at different temperature thresholds as the croissant heats up during baking. Proofing, the final rise before baking, determines the size and distribution of gas bubbles. Optimal proofing takes 2 to 3 hours at 24 to 26 degrees Celsius, allowing yeast to produce CO2 that inflates the dough. Yeast fermentation converts glucose into ethanol and carbon dioxide through this chemical equation. Underproofed croissants have small, unevenly distributed gas bubbles, resulting in dense texture. Optimally proofed croissants have larger, evenly distributed bubbles that create the perfect light, airy texture. Overproofed croissants have oversized, merged bubbles and weakened structure, leading to collapse during baking. You might ask, why does overproofing cause collapse? The answer lies in gluten network breakdown. Extended fermentation allows proteolytic enzymes to break down the gluten network, weakening its ability to contain gas pressure. Croissants are anisotropic materials, meaning their properties differ based on direction. The elastic modulus, parallel to the layers, E parallel, exceeds the elastic modulus, perpendicular to the layers, E perpendicular. The layer structure creates directional properties. The material is strong along the layers but weaker perpendicular to them. This anisotropy is crucial to achieving the characteristic flaky texture. Layers separate easily perpendicular to their plane but resist shearing along their length. Croissants are also functionally graded materials, with properties varying from exterior to interior. The exterior crust is hard, crispy, and dark from Maillard reactions. The interior is soft, moist, and light, creating a gradient of properties. The density of the crust exceeds the density of the core due to water loss and structure collapse. Moisture content varies from approximately 5% at the exterior to 25% in the interior after baking. During baking, the surface reaches about 200 degrees Celsius, while the core reaches only 95 degrees Celsius. The interior structure of a croissant resembles a solid foam, with gas cells separated by thin walls. The relative density equals the foam density divided by the solid density, typically ranging from 0.2 to 0.4 for croissants. The foam structure consists of gas cells connected by thin struts of baked dough, similar to engineered metal or polymer foams. The elastic modulus of the foam scales with the square of the relative density, following Gibson-Ashby foam mechanics. We can use scaling laws to predict croissant behavior at different sizes. Baking time scales with the square of the characteristic length L, following heat diffusion scaling. If you double the size of a croissant, you must quadruple the baking time to ensure the interior reaches proper temperature. A small croissant baking in 15 minutes would require 60 minutes if scaled up by a factor of 2. Let's examine the energy balance during the baking process. Total energy input equals sensible heat to raise temperature plus latent heat for water vaporization. Latent heat equals mass times the latent heat of vaporization, which is 2,260 kilojoules per kilogram for water. For a 100-gram croissant containing 35 grams of water, approximately 80 kilojoules of energy goes into vaporization alone. Understanding failure modes helps perfect the croissant production process. Layer collapse occurs when butter melts before water vaporizes, destroying the laminated structure. Butter leakage happens when temperature exceeds 20 degrees during lamination, causing butter to soften and leak out. Dense texture results from underproofing or insufficient water content to generate the steam needed for layer separation. Let's work through a quantitative example to understand the scale of transformations. Consider a croissant with initial dough volume of 150 cubic centimeters. At 35% water content, this contains 52.5 grams of water. Using the ideal gas law, we can calculate the steam volume at 100 degrees Celsius. The number of moles equals 52.5 grams divided by 18 grams per mole, giving 2.92 moles. Calculating the volume. 2.92 times 8.314 times 373 divided by 101,325 equals 0.089 cubic meters or 89 liters. This enormous volume of steam expands the croissant by a factor of 2 to 3 times its original volume. Croissants demonstrate principles used in advanced materials engineering. The laminated structure resembles aerospace composites, while the gas-filled structure parallels metal foams used in energy absorption. Both croissants and composites use layering to achieve high strength-to-weight ratios through controlled interface properties. Bakers optimize multiple variables to achieve perfect croissants. 6 primary variables form an interconnected optimization space: temperature, time, number of folds, butter quality, proofing, and hydration. Each variable affects multiple outcomes simultaneously, creating a complex optimization problem that bakers solve through experience. Industrial and artisanal production methods create different croissant properties. Industrial croissants use more layers with thinner spacing and shorter fermentation. Artisanal versions use fewer, thicker layers with longer fermentation. Industrial production takes 3 to 4 hours total, with highly consistent quality through precise control. Artisanal production takes over 24 hours with more variability, but potentially superior flavor complexity from extended fermentation. Let's summarize the key scientific principles that underlie the production of croissants, a delicious and complex pastry that combines lamination, gluten network development, and gas-driven puffing. Croissants are an excellent example of how materials science and physics can be applied to understand and optimize a traditional food product. By controlling variables like lamination, proofing, and baking, bakers can create a wide range of textures and flavors. The science behind croissants is a fascinating topic that can help us appreciate the art and craftsmanship that goes into creating these delicious pastries.